Hey everyone, welcome to this explainer. Usually when we hear the word error, we immediately think, uh-oh, I broke something, or I totally bombed that test, right? But today, we're actually going to completely reframe that word. We're looking under the hood of experimental physics, and spoiler alert, it is absolutely not about being perfect. It's really about becoming a master detective of uncertainty.
Okay, let's dive right into this with a pretty incredible quote from the source material. It says, "A measurement without an uncertainty estimate is scientifically incomplete. It is like a sentence without a period." Basically, in physics, an error isn't a failure at all. It's just this incredibly honest mathematical acknowledgement of reality's limits. Honestly, without it, you aren't really doing science. You're kind of just guessing.
So, to guide our little detective's journey here, we've got a roadmap. We're breaking this down into 6 parts. First, the philosophy of error. Then, accuracy versus precision. After that, the anatomy of error, followed by the math of uncertainty. Then we'll look at propagating measurement errors, and we'll wrap up the whole shebang with the future of metrology.
All right, kicking things off with part 1, the philosophy of error. Why imperfection is the language of truth. Now, the absolutely crucial thing to grasp here is that no measurement is ever exact. Literally never. Whether you're just a student measuring a block of wood with a cheap plastic ruler, or you're one of those world-class physicists at LIGO detecting microscopic gravitational waves, where, by the way, the displacement is thousands of times smaller than a single proton, there is always a limit. And that brings us to a really core term, the measurand. This is just the specific quantity you're actually trying to measure. But see, finding the measurand isn't just glancing at a number on a screen. It's this whole complex process of comparison, mediated by an instrument and interpreted by an observer, us. And every single link in that chain, it introduces some potential uncertainty. Moving right along to part 2, accuracy versus precision. Basically, hitting the bullseye versus hitting the exact same spot.
So what does this all mean? What is a true value anyway? In everyday conversation, you and I probably use accuracy and precision like they mean the exact same thing, right? But in physics, dismantling that misconception is step number 1. Think of a dartboard. Now, what's really interesting about this is how precision is all about repeatability. If you throw 5 darts and they all land tightly clustered together way up in the top right corner, well, you're highly precise. But you aren't accurate because you completely missed the center. Accuracy is about hitting the actual bullseye. So the ultimate goal for an experimental physicist is to be both tightly clustered darts, dead center in the truth.
Okay, section 3, the anatomy of error. This is where we identify the culprits messing with our data. So what's actually pushing our darts off target? Beyond just, human clumsiness or dropping something, we need to categorize the specific suspects sabotaging our measurements. First up, we've got random errors. These are your bidirectional fluctuations, basically the noise. Sometimes they push your reading a bit too high, sometimes a bit low. But because they go both ways, you can actually reduce them just by taking a bunch of measurements and averaging them out. Pretty simple. But then we have systematic errors. Oh boy, these are far more insidious. They consistently shift all your results in one single direction. They are the unknown unknowns of the physics world. I mean, taking 1,000 measurements with a ruler that was manufactured an inch too short, that's never going to get you closer to the true value, no matter how much you average it.
So where do these sneaky systematic errors hide? Well, they come from instrument calibration issues. They come from drift over time, as your electronics start to age. They can even come from environmental effects, like picture the thermal expansion of a metal ruler on a really hot summer day. They also come from parallax errors if you're just looking at a dial from a weird angle. And maybe the wildest one, loading errors. This is where the mere act of measuring something actually alters the thing itself, like a really cold thermometer cooling down a tiny drop of hot liquid just by touching it. Eliminating all these, it takes incredibly careful cross-checking and just absolutely brilliant experimental design.
Which brings us to section 4, the math of uncertainty. Here's a statistical toolkit we use to crack the case. All right, so because random errors are statistical, kind of like the roll of a die, physicists rely on a pretty heavy-duty mathematical toolkit to bring some order to those seemingly chaotic fluctuations. Basically, when you combine a ton of small, independent random errors, you get the Gaussian or normal distribution. Thanks to something called the central limit theorem, this famous bell curve literally shows up everywhere in nature. The big takeaway for us here is the 68% rule. If you take a bunch of measurements, roughly 68% of them are going to fall within 1 standard deviation, or 1 sigma, of your mean. It is the absolute standard metric for figuring out statistical confidence. But you might be wondering, just how high do the stakes get?
Well, in particle physics, you definitely don't just want 1 or 2 sigma. You want 5. To put that into perspective, 99.99994% is the confidence threshold for a 5 sigma discovery. That means the probability of your result just being some random fluke of background noise is roughly 1 in 3.5 million. No way, right? And that exact, incredibly strict threshold is what physicists at CERN famously used back in 2012 to confidently tell the entire world, hey, we discovered the Higgs boson.
Let's move into Section 5, Propagating Measurement Errors. This is all about how errors compound when you start combining measurements.
So it's one thing to measure a simple block of wood, but what happens when you use that highly uncertain length, width, and height to calculate its overall volume? Well, the errors propagate. They don't just magically disappear when you do the math, they tag along and actually compound according to some very strict rules. If you're adding or subtracting quantities, you just add their absolute uncertainties. But if you're multiplying or dividing, you have to add their relative uncertainties, so their percentages. And since these errors are usually independent of each other, physicists use this special trick called adding and quadrature. It's basically the Pythagorean theorem, but for errors, and it makes sure you don't wildly overestimate your total uncertainty.
Now, how in the world do scientists across the globe actually agree on combining all these different messy errors into one trusted number? Well, so the crucial point is they use the internationally agreed GUM framework. This ensures that a lab in Tokyo and a lab in Geneva are speaking the exact same mathematical language. It essentially categorizes uncertainty into 2 buckets. Type A is everything you can calculate using raw statistics from your repeated observations. And Type B covers pretty much everything else, like say checking the manufacturer's manual for your voltmeter, or just knowing the physical limits of your setup based on pure reasoning.
And finally, Section 6, the future of metrology. Let's look at how AI and quantum physics are totally redefining measurement.
We are currently standing right at the frontier of data science and quantum mechanics. And let me tell you, the traditional rules of the game are shifting rapidly. For starters, we're seeing this massive, game-changing shift toward the Bayesian approach to error. Instead of just treating probability as a simple frequency of events, Bayesian analysis treats it as a degree of belief that actually updates over time. It's a really elegant 1-2-3 narrative. First, you start with a prior belief based on past experiments. 2, you collect your shiny new experimental data. And 3, you mathematically update your belief using Bayes' theorem to get your posterior conclusion. It's a dynamic, constantly learning model of reality.
And then there's AI. Machine learning isn't just another tool in the toolbox. It's a revolutionary shift that's completely automating uncertainty quantification. We're now seeing physics-informed neural networks, or PINs, that actually have the fundamental laws of physics baked right into their code. It's wild. AI is out there identifying drift patterns to automate calibration, it's monitoring uncertainties across massive complex systems in real time, and it's even sniffing out those dreaded systematic anomalies long before a human ever could.
Which brings us to our final, ultimate question for this explainer. Can we ever measure the universe perfectly? I mean, even with the absolute best AI we can imagine, the answer is still no. And the crazy thing is, that's not because our technology is bad. It's because of the Heisenberg uncertainty principle. Quantum mechanics dictates a fundamental, inescapable, ontological limit to reality. The universe literally forbids us from knowing certain properties, like a particle's exact position and momentum, at the exact same time. At the deepest levels of reality, uncertainty isn't just some annoying error in an instrument. It is the fundamental fabric of nature itself. Just a little something to ponder the next time you pick up a ruler.